Hi there, Mr. Sutton bringing you the AB Calculus 414 classwork solutions on basic related rates. On this problem, we have a particle moving along the curve xy equals 10, and they're telling us x is 2, dy over d is 3. We want the value of dx over dt. This is a related rates problem. The dt kind of tips us off to that. So we need to take the derivative implicitly of this equation with respect to t. To do that, derivative of xy, we're going to need the product rule. So we've got x and y, whose derivatives with respect to t are dx over dt and dy over dt. Using my ribbon now, I've got y times dx over dt, and then I've got x times dy over dt equals derivative of 10, which is 0. So plugging stuff in, I've got dx over dt. That's actually what I'm solving for, so I'll leave it the way it is. Now for y, they didn't actually tell us the value of y, but we know that x times y equals 10, and they're telling us that x equals 2 at the instant in time where we're trying to calculate these things. So if x equals 2, we can write 2y equals 10, which means y equals 5. So we got 5 over here, plus x they told us was 2, and dy over dt they told us was 3. All that equals 0. So we've got 6. Subtracting that from both sides and dividing by 5, we've got negative 6 over 5, which gives us answer choice B. For this problem, radius of a circle is decreasing at a constant rate of 0.1 centimeters per second. In terms of the circumference, C, what's the rate of change of the area of the circle in square centimeters per second? So this is a related rates problem. There's a whole bunch of rates of change being thrown around here. Let's start with the formula for the area of a circle, because that's what we want the rate of change of. So we've got a equals pi r squared, and we're going to take the derivative of that with respect to t now. So we'll have dA over dt equals 2 pi r dr over dt. And where do we go from there? Well, the key on this one is that they want the answer in terms of the circumference c. And if you look at all the answer choices, there's a c in all of them. So one thing that's key here is realizing that the circumference, c, equals 2 pi r. 2 pi r is just another way of saying circumference. And we also know that dr over dt is 0.1, actually negative 0.1, because we're decreasing there. So just plugging all of that back in, we have dA over dt, that's the rate of change of the area, equals negative 0.1 times c. And that actually matches one of the answer choices. Choice B. For this problem, the volume of a certain cone for which the sum of its radius and height is constant is given by this formula here. The rate of change of the radius of the cone to respective time is 6. In terms of r, what's the rate of change of the volume of the cone with respect to time? So we've got different rates of change involved. This is a related rates problem. So we're going to start by implicitly differentiating with respect to t. Now before we do that, I'm just going to make my life a little bit easier and distribute this expression to the 10 minus r. So I'm going to call this 10/3 pi r squared minus 1/3 pi r cubed. And now taking the derivative of each term here. So first off, we've got dv over dt. And now that's going to equal, let's see, this is going to be 20/3 pi, or 20 pi over 3 times r, dr over dt. We're differentiating with respect to t, so everything gets a tail here. And then over here we've got pi r squared dr over dt. Time to plug in what we know now. The final answer is going to have an r in it, so we don't have to worry about substituting for that. But we do need to get rid of this dr over dt. We're told that the rate of change of the radius is 6, so we're going to put a 6 in for there. So we've got 20 pi over 3 r times 6, pi r squared times 6. And at this point, we just have to simplify this to look like one of the answer choices. So over here, let's see, 6 divided by 3 is 2, so this is 40 pi r. And over here, this is going to be minus 6 pi r squared. And we can't combine those, so let's just look for this in one of the answer choices. It looks like E is what we're looking for. On this problem, we're given an isosceles right triangle with an area of 1/2 s squared, where s is the length of one of the legs. At the instant when s is radical 32, the area of the triangle is increasing at a rate of 12. At what rate is the length of the hypotenuse of the triangle increasing at that instant? This is a related rates problem. We've got different rates that are in the same problem, and we have something happening at a specific instant in time. So we're trying to figure out basically dH over dt, the rate of change of the hypotenuse. So we're going to have to get a formula that has the hypotenuse in it. Now, since this is an isosceles right triangle and the legs are both s, we can actually use the Pythagorean theorem here. We can say s squared plus s squared equals h squared, so then h equals the square root of s squared plus s squared. Or, if we add these together, this is the square root of 2s squared, which we can simplify to s radical 2. So h equals s radical 2. That's our formula that ties things together. Implicitly differentiating this now with respect to time, we've got dH over dt equals ds over dt radical 2. And this is great as far as it goes, but we don't know the rate at which the side length is increasing with respect to time. To get that, we have to go back to this area formula, because they told us the rate that the area of the triangle was changing at. So if we can differentiate this area formula implicitly, and then maybe use the rate of change of the area, we might be able to find ds over dt that way. So I'm going to go to my area formula, and differentiating this, I've got dA over dt equals 2 times 1/2 is just 1, so we have 1s ds over dt. So there's the ds over dt that we want to get. That means we need to know dA over dt and the side length s. Well, we do know all that. They told us dA over dt was this 12 here, and then s, that's the side length, that's radical 32. So if I want to get ds over dt, I just have to do 12 divided by square root of 32. And I could simplify that, but I'm not going to bother doing that at this point. We're just going to plug this back in over here. And now I'm going to simplify this as much as I can, because I don't see this in any of the answer choices. So there's a lot of ways you might go about this, but since I've got one radical divided by another radical, essentially, I can move those things in together. So this is really like having the square root of 2 over 32, which is like having the square root of 1 over 16. Now the square root of 1 over 16 is 1 over 4. 12 times 1/4 is going to give us 3. That's 3 centimeters per second for units here. So that's going to give us answer choice B. For this problem, we're given three functions, w, x, and y, that are differentiable with respect to time. This is a key tip-off here that we're probably going to have to implicitly differentiate these with respect to time. But let's keep going. They're telling us these are related by the equation w equals x squared y. That's going to be important. And then they're giving us the rate of change of x and y, and also the exact values of x and y at a specific point in time. Given all this, we want to know the rate at which w is changing with respect to time. So let's differentiate this equation with respect to time. They're just kind of begging us to do it. This is a related rates problem. So we're going to have dw over dt equals, and now we're going to need the product rule for this. So we've got x squared and y, and this will be 2x dx over dt and dy over dt. Now we've got 2x dx over dt times y plus x squared dy over dt. And at this point, we're just going to plug in everything we have and see if there's anything else we're missing. So we have dw over dt equals 2 times x, which is 6, times dx over dt. Now they said x is decreasing at a constant rate of 1 unit. So that means dx over dt is going to be negative 1. And now y, they told us, was 20. Now for x, again, they said that was 6, so we got 6 squared. And dy over dt, they said that y is increasing at a rate of 4, so that's going to be 4. And at this point, we're just crunching the numbers. So we've got over here, let's see, this is going to be negative 12 times 20, so negative 240. Over here, we've got 36 times 4, which is going to be 144. So we got negative 240 plus 144. That's going to come out to, let's see, negative 96. And that's going to be, I guess, units per minute. So that gives us answer choice C. On this problem, when the area of an expanding circle is increasing twice as fast as its radius, what is the radius? So let's start by writing the area formula for a circle, since that relates area and radius. So A equals pi r squared. And since I've got different rates of change in the same problem, I mean, we've got the area's rate of change and the radius's rate of change. We've got related rates of change. Let's implicitly differentiate with respect to time. So we've got dA over dt equals 2 pi r dr over dt. And at this point, I'm solving for r, so I have to figure out a way of not having these other two variables around. Well, one clue to how I could do this is they said that the area is increasing twice as fast as the radius. That means that dA over dt has to equal 2 times dr over dt, which means that I can replace this dA over dt with 2 dr over dt. Now, at this point, I still have two different variables kicking around, so these dr over dt's, I can actually divide by that and cancel those out. Normally, I wouldn't be allowed to divide by a variable, but I'm guaranteed that this is not going to be 0. Dr over dt can't be 0. How do I know this? Well, they said that we have an expanding circle. That means the radius must be increasing, which means it can't be 0. It has to be positive. So all I have to do at this point then is divide by 2 pi. That'll give me 2 over 2 pi, which is 1 over pi, giving us answer choice C. On this problem, we have the radius of a circle that's increasing, and at a certain instant, the rate of increase of the circle is numerically equal to twice the rate of increase of its circumference. Based off this, we want the radius of the circle at that instant. So I'm going to write down the two relevant formulas here. A equals pi r squared, that's the area of a circle, and C, the circumference, equals 2 pi r. And we've got different rates of change involved here. We've got the rate at which the area is changing, the circumference is changing, and we have a relationship between the area and circumference rates of change. So I'm going to try to play into that relationship, and maybe I'll be able to do some substitutions and get an equation that just has r in it. Because ultimately on this one, I'm solving for the radius. All right, so let me implicitly differentiate here because I know a little bit about the rates of change in this problem. So for this one, we can write dA over dt equals 2 pi r dr over dt. Over here, we've got dc over dt equals 2 pi dr over dt. And where can I go from here? Well, they told me that the rate of increase of the area is numerically equal to twice the rate of increase of the circumference. So they're saying dA over dt equals 2 times dc over dt, which in this case, since this is dc over dt, we can say that the rate of change of the area is equal to 4 pi dr over dt. Well, we can substitute for the dA over dt over here with this 4 pi dr over dt. And what we've done at this point is gotten rid of everything except dr over dt's and r's. Now, another key on this one, to eliminate the other remaining variable in here, is that dr over dt has to be a positive number. How do we know that? Because they told us at the very beginning, the radius of a circle is increasing. That means it's positive, which means that it's not 0. So that means we are allowed to divide by it. Let's go ahead and do that. So we can write now just 4 pi equals 2 pi r. And then dividing by 2 pi, we get radius equals 2. And that gives us answer choice D. On this problem, radius of a sphere is decreasing at a rate of 2. At the instant when the radius of the sphere is 3, what's the rate of change of the surface area? And here's our surface area formula, 4 pi r squared. So we're going to start by implicitly differentiating this formula because that has rates of change of surface area and the radius in it. So this is going to be ds over dt equals 8 pi r dr over dt. And at this point, now that we've differentiated that, we're ultimately solving for the rate of change of the surface area, ds over dt. So hopefully we know what r and dr over dt are. We actually do. R is just what the radius is at this instant. That's 3. dr over dt, that's the rate of change of the radius. Careful though, they said that the radius is decreasing at a rate of 2 centimeters per second. So that dr over dt is going to have to be negative 2. So then just multiply all this out. We've got, let's see, this is going to be negative 6 times 8 pi. That's negative 48 pi for ds over dt. And that's centimeters squared per second because this is surface area's rate of change. So that's going to come out to choice C.